Yeah. So are there any questions? I mean, so just to recap, actually I will do this theorem today. I kind of delayed by making some mistakes. But what we want to get to is the following question of three-way elections. So there are three candidates, ABC, and there are n voters. So one proposal how to decide among them is to conduct three pairwise elections, A versus B, B versus C, and C versus A, and somehow put together the results to get a decision among three candidates. Okay, and so A versus B, the voting is, let's say, x1, x2, xn. That means the first voter votes +1 if he or she prefers A to B and -1 otherwise, and so on, x to 2. So +1 is for the first candidate, -1 is for the second candidate. And then the votes are pulled together by the Boolean function f to get the decision f of x. X is this vector x1 up to xn. Similarly, B versus C is decided by votes y, y1, y2, yn. So the decision is f of y, and C versus A is z1, z2, zn, and the decision is f of z. So one case where the decision is unambiguous, I mean, in fact, in this proposal, that's the only case where it is unambiguous. There are two possibilities. So if one of them wins against two others, okay, if let's say A wins against both B and C, then A is the winner. Okay, you can even order them. B versus C will tell you who is the runner-up, but we don't care. We want a winner. And if A wins against B and C, then unambiguously A is the winner. And same for if any one candidate wins against the two others. What else can happen? The only other way is that each one wins exactly one election, right? If nobody wins two elections, then each one wins one election. In that case, there are only two possibilities. A wins against B, B wins against C, C wins against A, or other way. B wins against A, C wins against B, and A wins against C. And both of these are ambiguous cases where you cannot decide. I mean, there is no decision who has won the overall. There is no reason to say one of them has won or not. Okay, and that is the undesirable situation. So in the first case where one of the candidates wins two elections, we say that that person is the Condorcet winner. Condorcet is the person who proposed this scheme. So Condorcet winner. And if not, there is no Condorcet winner. So question is, will there be a Condorcet winner or not? There is a very trivial case even with a single voter. So, okay, so far, one assumption I will recap, that if there was a single voter, then we will assume that there will be an unambiguous answer. In other words, a single voter is not going to vote x1, y1, z1 is not going to be 1, 1, 1 or -1, -1, -1. Okay, either of these would be leading to the stupid situation that the first voter prefers A to B, B to C, C to A. It means even if you leave it to the first voter, he or she cannot decide whom to pick out of ABC. Okay, so we'll assume that this is not the case. So for each voter has a clear preference. In other words, another way to say it, as I explained last time, each voter has a clear preference among ABC, one of 6 possible permutations. Okay, and then the theorem that we wanted to, so this is the assumption which I called assumption A. And Ayer's theorem says is that under that assumption that each voter is voting each voter has a clear preference. Even then, if there is some Boolean function, whatever decision-making rule you pick, if it always has a Condorcet winner, then that must be either the dictator function, a dictator function, or an anti-dictator function. Okay, for some k, it is f of x is xk for all x, or minus xk for all x. So this is the statement of Ayer's theorem. Now the point is to prove this, and before that, are there any questions or any points unclear about the setting? It's okay? Okay, so if so, then let me proceed. The proof will proceed by, we are supposed to show they exist, right? I mean, so they exist. So what we will do is a kind of, so to speak, probabilistic proof where we just calculate, we make these xi, yi, zi, all these will make them random, okay, over all possibilities, but ruling out this one. Ruling out this one, we will put equally random over all possibilities except this. In other words, it's a counting problem if you want. So you can call it probability. It's a counting problem, but probability language is useful sometimes, many times. So this one, we will make it random and actually calculate the probability and show that it is strictly positive, that probability that there is no Condorcet winner. Okay, so then that means that unless f is one of these functions. Okay, so that's going to be the proof. Okay, so now let me give the proof. Okay, so pick xi, yi, zi uniformly at random from the -1, 1 cube, except those two equal situations, 1, 1, 1 and -1, -1, -1. Okay, so there are 6 possibilities. So there are 1/6 probability for each tuple. And independently, for different I, choices are independent. For different I, we pick them independently. Okay, so this is same as uniform distribution on all possible plus minus ones here, subject to the following condition. Okay, so there are 6 to the power n possibilities, and we are picking all of them equally at random. Okay, so that is what we do, and now we will under this we will calculate the probability. And now we will calculate the probability. So what is the probability that there is no Condorcet winner? So that depends on the decisions fx, fy, fz. And exactly the same way, if all of them are equal, that is when we are in doubt. If fx, all of them are 1, then a is preferred to b, b is preferred to c, c preferred to a. And if all of them are -1, it's the reversal. But every other possibility is fine. Okay, so the only y is no Condorcet winner is same as probability that fx equal to fy equal to fz. Okay, we have to calculate this probability that fx equal to fy equal to fz. F is a fixed Boolean function. We have fixed some f, and then we work this out. Now, how to calculate this probability? So we will. This is where Fourier analysis will come. It is convenient to write this in a nice way as an expectation. So I will write it and then explain. This is same as expectation of 1/4 plus 1/4 fx fy plus 1/4 fy fz plus 1/4 fz fx. Okay, why is that? Each of these is plus minus 1, right? So just take any three plus minus 1. So if all of them are equal, then these three products are 1, 1, 1. So you get 1/4, 1/4, 1/4, 1/4. This total will be 1. What if they are not all equal? Then two of them will be equal and the other one will be different. So let's say fx and fy are equal and fz is different. Then fx, fy, this will be plus 1, whereas two of them will be -1, right? So if they are not all same, then two of these will be -1 and one of them will be +1, and you get complete cancellation. 2 1/4 and 2 -1/4. So this is 0 or 1. So this whole thing is 0. I mean, okay, I don't need to. This whole thing is 0 if fx, fy, fz are not equal, and 1 if fx, fy, fz are equal. So this is just a convenient way to write it. Okay, but now by symmetry of the whole thing, so 1/4 is fine. That's the expectation. Other three are identical. Okay, so x, y, z, they are like this, but their fx, fy expectation will be same as fy, fz expectation. The relationship between the three things are exactly same. So let's just write it as expectation of fx into fy. Okay. So what is this? What is this expectation of fx, fy? So we calculate that using Fourier. Okay, so write f of x as f hat of s chi s of x, right, over s. And fy is similar. Chi s of y, take the product and expectation. So what is expectation fx into fy? So we'll get 1/2 to the power n from this outside, and then we take a term corresponding to s there and a term corresponding to t here, and we get f hat of s, f hat of t, expected value of chi s of x, chi t of y. Okay, so this is what we get. So this expectation is what we need to calculate. Okay, so what is this expectation? So let me do that calculation on the side. This is just expectation. If I is in S but not in T, then chi s of S is the product of, so chi s of X is the product of Xi over I in S. So those I in S but not in T, you will get an Xi. And those I in T but not in S, you get a Yi, because then they come here, product Yi, I in T. And then for those I which are in S intersection T, we get both Xi and Yi. Okay. Now this factors, these are all across I, there is independence, right? So you get product over I in S slash T, expectation Xi, product over I in T slash S, expectation Yi, and product over I in S intersection T, expectation of Xi Yi. Now the thing is, expectation Xi, each Xi is unbiased. Okay, it is equally likely to be +1 or -1. So these things are 0 unless S is equal to T. If S is not equal to T, then either S slash T or T slash S is non-empty and you will get a 0 factor. So you get 0. So only when S equal to T we get something. So when S equal to T, what do we get? Across I it is the same. So it is expected value of, let's say, x1 y1 to the power of the cardinality of S, if S equal to T. Okay, is any questions about this? Is it okay? So I just calculated the expectation of product of two characters, one applied to X, another applied to Y. Okay, and that gives me this, and if S is not T, we see a singleton hanging out, that will give you 0. Otherwise you will get expectation x1 y1 to the power cardinality of S, because all of them will be across I identical distribution, right? So what we assume is okay, so we'll pick xi yi. So this is assumption B. I didn't write it, but that's what we are doing. Xi yi zi are picked uniformly randomly from these things. Okay, so what is expectation x1 y1? We can even calculate that explicitly. Under this, what is the expected? What are the possibilities? Okay, so what are the possibilities? So if I write here So for x1, y1, z1, there are 6 possibilities. Okay, I'll write as plus plus minus, or plus minus plus plus minus minus, and then similar with minus plus plus minus plus minus 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 plus. These are the 6 possibilities, right? So what is x1, y1 in each of these? In this case it is plus, in this case it is minus, 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 here it is plus. So expectation of x1, y1 is actually minus 4 plus 2 divided by 6, which is minus 1 by 2. Okay, so that's the expectation, elementary calculation. So we are picking uniformly from all these possible 6 vectors. Therefore, we get minus 1/3. So I come back here, and this is actually equal to minus 1 by 3 to the power of cardinality of S. Because these x1, y1, z1 are supposed to be not all equal, there is a negative correlation. That's why you're getting minus 1/3. Anyway, so coming back here, stop me at any time if the calculations, they're elementary, but I may jump over something without explaining. So please stop me. Otherwise, I'll just continue. So here we have 1 by 2 to the power n. Now we have seen that if s not equal to t, we get nothing. So only over s, and then we get f hat of s squared, and then minus 1 by 3 raised to the power of absolute, cardinality of s. Okay, so this is what we get. So this is so now we have an expression, Fourier expression for this probability. Going back to this, so what is this probability now? Let's write this probability. So this probability is, I continue here, 1 by 4 plus 3 by 4 into 1 by 2 to the n summation f hat of s squared minus 1 by 3 to the power of cardinality s over all s subsets of 1 up to n. Okay, so that is what we get. So now now we bring an inequality. This is the only inequality step, and we'll see. So what we can say is that I will say, minus 1 by 3 to the power of cardinality s. What is the lowest number it can take? It is greater than or equal to minus 1/3. Right. So because cardinality s can also be 0, but in that case it is positive. Okay. So when cardinality s is even, this is a positive number, so greater than or equal to minus 1/3. When it is odd number, the lowest odd number is 1, and that gives you minus 1/3. Later ones will give you 1 by 3, 27, minus 1 by 27, and all that. So this is all we say. So if I do that, then I get this is greater than or equal to 1 by 4 minus 1/3 cancels. I get 1 by 4 into 1 by 2 to the n summation f hat of s squared. Okay, this is, by the way, L2 norm squared. It is just 1 by 4 minus 1 by 4 into L2 norm squared of f by 2 to the n. Remember, my L2 norm is with counting measure. It's just the sum of fx squared. So what is this actually? This is actually 1 by 4 minus 1. This is 1. F is 0, 1. If s plus minus 1 valued. So f square is 1. So if you sum, you get 2 to the n. That makes it 1. So this is 0. Okay. Is it okay? So I use Plancherel here to say summation f hat of s square is same as summation f of x square, and that is 1 because f is a Boolean function. So it is plus minus 1 valued. So we got Okay, so probability greater than equal to 0. Not a profound statement, but we'll analyze when the equality can be achieved. That is the whole point. So we got that this probability is greater than equal to 0, and there is exactly one place where equality and inequality comes. So when can equality be achieved? So that means the probability is 0 if and only if. You have to analyze this step. This is the inequality step. What is the inequality we use? We use this one, 1 by minus 1 by 3 to the cardinality s greater than equal to. This is strict unless cardinality s is 1. If anything else, the inequality is strict, right? It's only cardinality equal to 1 when you have this equality. So that means here to go from here to here to have equality, all those terms should be 0. So f hat of s equal to 0 whenever cardinality s is not equal to 1. Okay, whenever cardinality s is not 1, this should be 0. So what does that tell us? We are close but not done actually. So what does this mean? So this is same as saying, so imagine a function which is, so this means just so what is f? I have written the Fourier expansion x here, right? Fx is 1 by 2 to the n by 2 f hat of s chi s of s. Now we see only singleton sets are there. So that means it is a linear combination of chi 1, chi 2, chi k. So I'll just write fx is a1 x1 plus up to an xn for some ai in R, because chi sub I is just that. Chi sub I of x is xi. So we get only those, so it is a linear combination of characters for singletons. Therefore, it must be of this form a1 x1 plus up to an xn for some ai's which are real numbers. So so this is not quite what we want, right? What we want to show is the probability is 0 if and only if f is a dictator. That means there should be only one non-zero coefficient. So how will that come? Why will that come?
Is plus minus 1 valued, maybe that will.
Yeah, so that's the key point. So it's not any real valued number function, but it takes only values plus minus 1, right? Therefore, so linear combinations, can they be really plus minus 1 valued? We just have to check that it's not possible. So we claim that if even two coefficients, suppose two coefficients are non-zero. Okay, so then a1 x1 plus a2 x2. Let's write the possible values. Okay, so just look at this one. a1 x1 plus a2 x2 can take values if both are minus 1, minus a1 minus a2, or minus a1 plus a2, or a1 minus a2 and a1 plus a2. Okay, so it seems to take 4 values. Actually, they can be equal also. If a1, a2 are equal, these two are 0, right? The claim is there are at least 3 are distinct. At least 3 are distinct among this. So you see, these two are anyway not equal. Minus a1 minus a2 minus a1 plus a2 are not equal because a2 is not 0. Similarly, a1 minus a2 and a1 plus a2 are not equal because a1 is not 0. So these two are distinct, these two are distinct. So we have 2. Now, can we have equalities here? Okay, if these two are equal, that means a1 equal to a2, in which case this and this are going to be distinct. So anyway, so you just check. I will leave it to check. It's just a little case by case analysis. So it's possible if a1 plus a2 is 0, these two can be equal, but then these two will be unequal and different from those two, and so on. or these two can be equal and these two different. So at least 3 are going to be distinct. So that proves that that is for if 2 are non-zero, but then the rest will only add to your range, right? You can fix all the other xi's and see that you will get at least 3 values. But f is, so then range of f has at least cardinality greater than equal to 3. But f is Boolean. So the conclusion is that there can't be 2 non-zero coefficients. There is only 1 non-zero coefficient. Exactly 1 ak is not equal to 0. Okay, so then it's Boolean. So it's ak xk, that's all, but it is Boolean, implies fx has to be xk or fx has to be minus xk. These are the only 2 Boolean functions of the form ak xk. So that's the conclusion. So if the probability is 0 for no Condorcet winner, then f is either the dictator function or the anti-dictator function. So that completes the proof.
So Manju, this argument about A1 and A2 not 0, I wonder if you can do it easier if you just use the linear independence of these monomials x1, xn. Can you do that? Because it seems that they are linearly independent on this thing, right?
They are linearly independent. Yeah, probably you are. I mean, so you can say it that way also. The set where this is z. No, what is it that you want to say?
So 1, x1, x2, xn are linearly independent in this space. So if you can write them as a combination.
But you have to show no Boolean function is there, right? In that span. That's what I mean. It is there, but only if you take one non-zero coefficient.
Yeah.
Okay, I don't quite see the argument.
Okay.
Are you suggesting a specific argument?
No, I will. Yeah, I mean, I don't have the full details, but I was just thinking just to nail that maybe linear independence might be okay. I don't know the full argument.
No, maybe right actually. So the set of the vector. So you are working in the vector space Z2 square. So that I guess, and then you can maybe you can make an argument. Yeah, I didn't think that way. Quite possible. Yeah. So this is the argument I came up with. I don't know, but there may be a simpler one. Yes. Any other questions, comments here? Okay, so if not, so this is a nice theorem that we have proved that this is actually so if you don't have a Condorcet winner, then sometimes if you don't have, or rather if you always have Condorcet winner, then it must be a dictator function. Okay, so and in fact one conclusion is actually nice, so maybe it is worth writing it out separately. So note, because we will use it. We did not merely, so under assumption B, we have actually calculated the probability. Assumption B is that xi, yi, zi are uniform on this 6 tuples, the 6 possible tuples, right? Under assumption B, we have shown that probability no Condorcet winner is exactly, we have found an expression. It is 1/4 plus 3/4 into 2 to the n sum over s f hat of s squared into -1/3 to the power of s. So there is a meaning to this. So there is a. So did I introduce stability? I did mention that. So one can write this in terms of stability if one wants. So this expression is all we want, but since Soumyendu asked some question and I had defined. So you may recall that stability of a function was defined as expectation fx fy, okay, where x is chosen uniformly on z2 to the n. We pick a random point, that is how x is, and y is constructed in the following way. It is taken to be xi with probability is probability what? Yeah, or rather, let me just yeah. So okay, I can write like this and then refreshed with the remaining probability. So what is that probability? Is it rho or? Okay, so this one I have to think, because so the other way to say it is, let me say it the other way, then maybe we can figure out. Another way to say it is xi yi independent across I. Okay, and all of them are unbiased. But xi and yi are correlated, and that correlation is this number rho. Okay, so if I do that, is this the right one or is it, this is not the right one, right? So this is maybe
say rho by 2.
Yeah, is it rho by 2? Maybe. Actually, it doesn't make sense because rho can also be negative. So maybe it is, okay. So that suggests what it must be. So let's just see. Is it half plus rho by 2? And half minus rho by 2, is that, does that make sense? So in that case, what will be expectation xi yi? It will be, so under this expectation xi yi is going to be, if this happens, when I say with probability, it means you make a coin toss independent of everything else to decide this. So this will be 1 in this event. Also, with probability half, it will be the same. So it will be half of. Okay, it's not making sense actually. This is giving some gibberish. So no, this is, oh, sorry, minus. Sorry, expectation xi yi on this will be 0. So okay, so then it's not what I'm saying. So hold on. This will be 0. So okay, so this is giving me half plus rho by 2. Here I am saying rho, which is the one I should take.
Maybe you want yi equal to xi with that probability and minus xi with the other probability.
So then will it be rho? I mean, half plus rho by 2 minus of this, that will make it rho, right? Okay, you're right. So that seems to work. Okay. So if I do minus xi, then the probability expectation yxi positive in this case, negative in this case. So it will be minus of half minus rho by 2, which will give it rho. Okay, excellent. So that's correct. Thanks. So this is the correct one. So these are two alternate descriptions of the same thing, how they are correlated. And but yeah, but what is it? The stability. This is measuring the stability of the function. In how you should think is, if f is a, this can be defined for any real valued function, complex valued function. But for Boolean functions, this is +1 or -1. So basically, it is checking the probability sort of. It's not the probability, but maybe half plus the probability by 2, whatever. That what will f change if in xi? So if some coordinates are changed with this problem, think of rho as being close to 1. If think of rho as being close to 1, then this is close to 1. This is a small probability. So with a small probability, each coordinate is flipped. Will the function value change or will it be unperturbed? That is the question. So that is measuring the stability of the function. So with that, actually, so by the type of calculation that I showed, you can check that this is actually, so this is an, you can take it as exercise. It is similar to the one that I had here. I did some calculation here, but note that this x and this y, okay, it's actually the same calculation, okay? It's actually the same calculation, so it's not even an exercise. It comes out exactly the same way, except their expectation xi yi was minus 1/3. Here it will be generally 1/3. So this will be f hat of s square times go to the cardinality of s, and there is a 1/2 to the n outside. Okay, so this is what it will come out as. Okay. Okay, so this is, so in that sense, this is actually stability minus 1/3. So this is if you want to write it in that language, then this probability is 1/4 plus 3/4 into stability minus 1/3 of f. Okay, so that's what I mean. I don't I will not have, in what I do, there will be no particular advantage in writing it like that, but I just wanted to make a link to these other concepts. Okay, so this is the thing. But we'll use this probability expression for in going further. Any questions, comments here? Actually, do you think that this is any interesting theorem? I mean, is it,
what was the problem with your first formulation, that you keep it xi with probability rho and
oh, there the expectation xi yi was not coming out as rho. Expectation, yeah. So this will make it expectation xi yi comes out to be just rho.
No, in that case also it will be rho only, right? Xi yi will be xi square with probability rho, and if you refresh, it will be 0.
No, I had written, okay, if I had just put, but if I put rho negative, what is that? I mean.
No, but here also you are not taking rho negative, no? You are taking rho close to 1 or something. That's how
No, but you can take rho negative. Here you see stability minus 1/3. Rho can be taken in minus 1, 1.
I see.
Possible.
Okay, fine. Right.
Yeah.
Okay.
But so that's where I got confused. So to wanted to write with
one is the one with refresh.
Sorry.
The standard way you define is via this refreshing thing. That's why I got
yeah, but you can convert this to the refreshing part. Yeah, okay, I'll have to think. So
okay, no problem.
Yeah, so the probability that they are equal is less than half actually. So that is where the problem is. Rho is negative. Yeah. So maybe refreshing way cannot be written for that situation.
Negative, right. Okay.
Any other comments? But what is your take on this theorem? I mean, have we said anything of content or not? So you can take majority function, for example, and it is saying that there is no Condorcet winner. Okay. So here is an exercise I want to give. Actually, in itself, this does not have content. Okay. I mean, it will. So here is an exercise. Let F be majority. Take n odd. So let Pn be the probability that there is no Condorcet winner. See, all this is saying is that Pn is positive, right? All this, I mean, as stated, Pn is positive, but that is nothing. If Pn was going to 0, we would be happy, right? If Pn is going to 0, if this was the case, then what is the problem? It just means that in a large population with high probability, you will have a Condorcet winner. So we should be okay with it. You may worry about how fast it is going to 0, but if Pn were going to 0, then the conclusion that the conclusion is nothing. I mean, conclusion is, and then we are happy actually. Then in a large population, of voters, there is a Condorcet winner with high probability. With high probability. So, for example, if that is true for majority, then this theorem is completely irrelevant. In a finite situation, everything will have positive probability. That's not the point. But it so happens. So, what I give as exercise. So first, maybe you can do numerical, because it's plot Pn. Actually, it doesn't go to 0. In fact, it goes up to some number, which is approximately 0.09 approximately. So it is not it's nearly 0.1. Okay, so the probability, so this not having a Condorcet winner is not only not going to 0, this is actually increasing, but you plot it and see that it will actually converge to a number close to 0.09. It's maybe a little short of it. So it's actually a serious conclusion. I mean, we are not, majority function will not work. So in fact, even so in O'Donnell's book, he says he gives theorem also that if you take any symmetric function which uses all the voters equally, then the Pn you cannot is not going to be small. I mean, it will be something. Okay, it's but anyway, here the next exercise to do it analytically. This Pn has an actual show that Pn in fact converges to, let me just check the number. Okay, so in my notes I have written it. It's again, it's a calculation one can do, but that requires a little more thinking. I will tell you what the it is. It is apparently 1 minus, okay, already I forgot, 1 minus 3 over 2 pi r cos minus 1 by 3, which is actually 0.0877. So this is the number, not 0.09, but this is the number to which it is increasing. So Pn actually converges to that. So this one, if you want to do, so think of central limit theorem. Okay, otherwise you may have difficult. I mean, analytically, the Fourier coefficients of majority function, you have it, but I don't think you can explicitly work with this expression. Probably not. If you can and get an exact expression, fine. But the limiting number is this one. So it is actually, the conclusion is serious. It's not that it's there is a significant probability. Okay, it's not overwhelming probability. There is a significant probability for this. If you go for a higher number of candidates, probably this type of problems will arise more. I actually didn't even think about it, and I don't know the answers there. If you go for a higher number of candidates, whether what is the scheme, etc., I haven't thought. Okay. Any questions here?
So, so when a lot of people's opinion matter, does that make the Fourier coefficient diffuse, and that's creating the problem?
Sorry, say it again. If this part I did not go into. So if many people, yeah. So what you say is true. What you say is true. Yeah, maybe that is in fact a good point. So so see, when dictator function, what it does is it puts all the weight on singleton sets. Okay, but if you are actually taking a lot of people's opinion, what Soumendra is saying is the following point, that this Fourier coefficients won't be supported on singletons. They will go to higher and higher cardinality sets. And then the inequality will become worse and worse. If you see in the proof, the inequality 1s 1 by 3 to the cardinality bigger than, this is becoming more and more serious inequality because you are putting on higher things. So in other words, the probability will be actually significantly bigger than 0. So that is a good point actually. That is true. That's probably the real mechanism by which it is happening. Okay. Any other questions, comments?
Manju, this instead of Boolean, if we have 3 candidates and we allow, say, 3 possibilities, and then we have a runoff, are such things being looked at, or they are just?
I don't know from the point of view of social choice theory, I know very little. I mean, I only know this application because it uses Fourier analysis. So, yeah, so certainly there are many other schemes one might come up with. Maybe Boolean analysis is actually useful there, maybe not, I don't know. So you are having a 3-way election straight away, and where they vote only for one candidate, is it?
Yeah, and then no, if nobody gets more than 50%, then there is a runoff between the top 2 fellows.
Yeah, but okay, for example, a simple majority is certainly a possible one. You just have a thing between 3 candidates and just do a simple majority, which is what our elections are actually.
Correct.
So that is certainly a reasonable possibility. But yeah, so drawbacks will be of the kind that the number of people who are happy may be less than the number of people who are unhappy. That's why you want a 50% cutoff, I guess.
That's right.
Yeah, so possibly there are such schemes. I don't know anything about them. Okay. Anything else? So what I want to now go for is something even more serious. So this is all fine, but so something like I earlier emphasized that, and I said that from point of view of analysis of modern times, people don't like delicate theorems. We like robust theorems or stability versions. Okay. So this is a conclusion that if the probability, so what is the other? So this is one possible objection one could have raised to this theorem, that, oh, come on, if you take majority Pn goes to 0, so it is not a serious difficulty, this theorem. But that is not true. Pn doesn't go to 0. So that is one resolution of one difficulty, one objection to this theorem. Here is another objection to this theorem, that this is not a robust theorem, in the sense that you are saying that if there is always a Condorcet winner, then f is a dictator function or anti-dictator function. Okay, so that is we accept that that is an undesirable voting scheme. We don't like dictators or anti-dictators, in the sense that you just do the opposite of what the dictator says. So neither of this is a good choice. So we don't like this scheme, let's say. So we don't like this scheme. Hence, this is, but what the theorem is not saying is, suppose I give up a certain small probability. Okay, I will give up a certain probability of getting a Condorcet winner. Can I find, we have seen that the majority is not good. Majority will lose a probability of 0.0877. But maybe there is a much more equitable scheme than the dictator, which achieves probability 0.999. Okay, is that possible? So let me repeat that again. This is saying that if you want a Condorcet winner always, then you have to go for dictators, which we don't want. But if we are willing to give up a certain small probability and we want only Condorcet winner to exist with probability 0.99, okay, can I find a different Boolean function which is much more equitable and achieves this, possibly? So I mentioned to you.
So you have a bunch of dictators that should work, I guess.
A bunch of dictators, how do they agree with each other?
Instead of the whole population, you do the Condorcet thing on a small set of size.
You can have a small set thing, but actually no, you can have a. So what you are saying is 2 people decide or something like that, right?
Yeah.
Even that will not achieve actually. Even that will not achieve. We will prove a stability version, in fact. So what I was objecting to is that this theorem is not saying it, but we will actually prove a stability version which will say that it has to be close to dictator function. If the probability of having a Condorcet winner is high, then your Boolean function has to be close to a dictator function. Okay, so this is the stability version. Is the statement I will mention now, but I hope the spirit of it is clear. It is similar to the other robust stability versions where I talked about in uncertainty principle. And this is the style of modern analysis which people should get used to. For every sort of thing, to these days, people are proving stability versions and so on. So you take anything in, so take any, any like isoperimetric inequality. Okay, isoperimetric inequality tells that if you the minimizer for a given volume, the body that minimizes the surface area is the ball. And this is supposed to explain why raindrops are spherical in shape. But in application, in the real world, there is no body actually. It is all R3 is an approximation to reality, and there is no exact ball, there is no exact minimization, etc. So a more serious question is, suppose there is a body which for a given volume almost minimizes the surface area. Is it necessarily close to a ball, or could it be a completely different shape like a torus or something? So that is what a stability version is. So the person who got, one of the analysts who got Fields Medal last time, Figali, he has worked on this kind of theorem. Just I'm mentioning that this appears to be the style of modern analysis, that people like these stability versions of theorems rather than even some old classical theorems, people are taking up and proving stability versions of it. So it's something to keep in mind. So now I come to
Manju, like looking at that picture of the numerical picture of Pn as a function of n.
Yeah.
Like if n is small, then it's close to 0. I guess that's what I was meaning.
No,
like
this part is that is 0. I don't know.
okay.
I will just So, but it increases. That seems to be the case.
Yeah, so I was meaning if like for n equal to 3, it was very close to 0, then you could take 3 dictators and took majority over them. And
No. N equals 3. Okay. If it was close to 0, no, it is. I think it is some strictly positive number. I think.
Okay.
Because majority is not the dictator. This theorem tells you that the probability is something strictly positive, right? So, I mean, you see that it is something strictly positive. What it is, I don't know. It may be a rather small number, but.
But I mean, in that case, I think you can write down if the explicit coefficients, right? Fourier coefficients for majority. I think they are half, and minus half. That's all. So.
Oh, is it okay? Okay.
That is, each of the coefficients of x1, x2, x3 is half, and then x1 times x2 times x3 is minus half. So you can easily compute that one.
Mm-hmm. Okay. So yeah, I don't know what the number will come out to be in the end. Yeah. So you're saying the singletons have half, and the triple will have half.
Minus half.
Minus half. Okay.
Yeah.
So that will make it, So, okay, I don't want to compute now, but it is, as you say, it is doable from here. Something, so one can find it. Maybe one should, part of the numerical exercise is to do the whole plot. From n equals 1 to maybe 20, 100, something, and see. Okay, so any other points? So I'll state the stability version now. Okay, robust stability version. So this is due to Gil-Khalai. Actually, this proof, by the way, this proof is also due to Gil-Khalai. This proof is, he's one of the people who revived the theory of Boolean functions in recent times, some 20, 30 years ago, sometime. So Khalai proved it, but I think, okay, I'm a little unclear. So the proof we are giving is maybe due to this. Friedgut, Khalai, and Asaf Nawar. all famous people. So what is the theorem? Okay, it says the following. Suppose, so is such that in a three-way election, I mean the same setting, so I will not write it again. In a three-way election, probability to using F, probability there does not exist a Condorcet winner is less than equal to delta. Okay. Suppose F is such that this is 2. So then the statement is there exists some k in 1 to n. Okay. So it will be close to that dictator. K will be the dictator. Okay. To which F will be close. But in what sense will it be close? And an exceptional set, let's call it E, contained in Z2 to the n, having cardinality small in proportion. Okay. Cardinality of E will be small. Maybe it is smaller than 10 delta 2 to the n. So in proportion it is small. Okay, its probability is only 10 delta. Such that Fx equal to xk for all x not in E.
It's 1 o'clock.
Or it is minus xk for all x not in E. Okay, I hope the spirit of the theorem is clear. So F is very close to a dictator function in the sense that outside a small set, this is a set of probability 10 delta if you want. In proportion, it's a small set in the whole of Z2 to the n. Outside of that small set, F is actually equal to the dictator or equal to the anti-dictator. Okay, it's not that sometimes it's this, sometimes it's that. It's either this or this. Okay, so since it's 1 o'clock, I will stop here. I will go to I'll give the proof next time. And after that, that's the last thing I will do on this Boolean functions. Then we will go on to prime numbers in arithmetic progression and stuff like that. Okay, stop the recording, but any questions, etc., I'll be happy to take.